Swayam Prabha. Digital India. Educated India.
I will have the equation as, let's say this is I1, I2, I3. I'll have the voltage drop across R1, which is R1, I1 minus I3, plus I had that plus Vx equals V1, but that Vx cancels with minus Vx, and here I have R2 times I2 minus I3 minus Vx, which cancels out, okay, equals V1 minus V2. And if you observe, originally I had the equation, KVL equation around this loop or this mesh, and the KVL equation around this mesh. So if I add the two, essentially what I have is a single KVL equation around this bigger mesh, which encloses the current source. Okay. This is nothing but KVL equation around this bigger mesh, which is called a super mesh. Okay, in analogy to supernode. So if a branch that is common to two meshes is a current source, what you do is you avoid that branch and you write the equation around a super mesh which encloses that current source. Okay, when you do that, the voltage across the current source will not be in the picture, and you will get this KVL equation in terms of all the voltage drops. So for instance, this is the voltage drop across R1. This is the voltage drop across R2, and on the right hand side you have the total voltage in the super mesh. Okay. Okay. Is this clear? Any questions? This is exactly analogous to what we do with nodal analysis and voltage sources. There we define a super node which comes out because of defining an auxiliary variable and cancelling out by adding two equations. Here we define the voltage across current source as the auxiliary variable, add up the equations for the two meshes, that auxiliary variable cancels out, and you will be left with a single KVL equation around the super mesh. Okay. Okay, now there is a question about non-ideal current sources. Now we have not discussed non-ideal current sources, but maybe we can quickly do that. See, as far as the analysis is concerned, a non-ideal current source will be the same as an ideal current source in parallel with some resistance. Okay, so for instance, in this case, you would have an extra resistance. Now, if you have that, then in case of mesh analysis, you will have an extra mesh and you have to write that. Okay. So when I write a current source like this with this symbol, it by definition means an ideal current source. Okay. If you have to depict a non-ideal current source, what you have to do is to have an ideal current source in parallel with a resistor. Obviously, now you have increased the number of components in the circuit. In case of nodal analysis, the number of nodes remains exactly the same. But you have an extra element, and in case of mesh analysis, if you have a resistance across the current source, you will have an extra mesh and you have to solve for it. That's all. Okay. So whatever we said so far will apply to this. The only thing is, if you know that the current source is non-ideal, you have to model it with two components, an ideal current source and a resistor. Okay. So I hope that answers the question. So now when you write the equation around the super mesh, you will have one less equation because for two meshes you wrote a single equation, and but you do still have three variables, I1, I2 and I3. Okay, so you lost one equation because you defined the combination of two meshes as a super mesh and wrote a single equation for these two meshes together. But you will get an extra equation which is the same as before, which is the definition of the current source. Okay. So I hope this is clear. Okay. So now we can again compare nodal analysis and mesh analysis. But when you have an extra, when you have a voltage source in nodal analysis, okay. So when you have nodal analysis with voltage source, first of all, if the voltage source is between a certain node, I'll call it node K, and reference node, you already know that node voltage. Okay. So you don't have to write an equation for that, and you can write the equation for the rest of the nodes. Okay. Similarly, if there is a current source along the periphery, then the mesh current is known. Okay. So again, you can remove this variable from the equations and use only the remaining mesh currents. Okay. Now these are for hand analysis. Usually for computer analysis, what you do is you don't have different things that you do for different cases. You would like to have a uniform algorithm that covers all the cases. So in that case, what you do is that you always, when you have a voltage source in nodal analysis, you define the current through the voltage source as an auxiliary variable and then go ahead with it. You don't worry about whether the voltage source is between some node and the reference node or between two nodes, etc. But while doing hand analysis, you reduce the number of equations, your job only becomes easier. So that's why you do this. Okay. And if you have voltage source between two nodes, you define a super node, which is the combination of the two nodes. And if you have a current source common to two meshes, when it's on the periphery, it belongs only to one mesh. When it belongs to two meshes, then you define a super mesh, which is a combination of two meshes. Okay. So again, the analogy between nodal analysis with voltage source and mesh analysis with current source is very clear. Okay, so you should be able to choose either one. Now, both methods will work for any circuit. For now, let's assume that all our circuits are planar circuits. Mesh analysis we know is applicable only to planar circuits. Now, my question is, let's say you have a planar circuit. Which one will you choose? Will you choose nodal analysis or mesh analysis? I would like opinions of the participants. So I opened a poll. You can register your vote for either mesh analysis or node analysis. Now this is actually I think you can now see the results. Okay, so most of you have chosen mesh analysis and I'm a little surprised. I would like to hear from you, those of you who chose mesh analysis, why you would choose mesh analysis over node analysis. What is the reason for choosing mesh analysis? Out of 11 people who answered, 9 people have chosen mesh analysis. What's the reason? Now, of course, we are talking only about planar circuits because the mesh analysis, the way we defined it, is not even applicable to non-planar circuits. Okay, now let's see what would be the basis of choice. Now, for node analysis, first of all, like I said, when we do nodal or mesh analysis, we first write for node analysis KCL equations and get the node voltages, and in case of mesh analysis, we get the mesh currents. After that, we still have some work to do, but that's rather trivial. Okay. In case of node analysis, to find branch voltages, you have to take difference between node voltages that you have calculated. And in case of mesh analysis, to find branch currents, you have to find differences between mesh currents that you have calculated. These things are quite easy, and I'm assuming it can be done quite easily. Okay. So the moment you solve the nodal analysis equations, we call the circuit to be solved, although we know that a little bit more work is required. Okay. Similarly, when you do mesh analysis, you solve for mesh currents, and after that there is a little bit of more work, but that's relatively easy, so it is solved. So the choice is based on the number of equations you have to solve. Okay, for node analysis, you have n minus 1 equations. So let's take a circuit with n nodes and b branches. Okay, so n minus 1 KCL equations for nodal analysis, and for mesh analysis it is b minus n plus 1 KVL equations. Okay, so this is what we need to solve. Now, which of these is likely to be more? Is n minus 1 likely to be more, or b minus n plus 1 likely to be more? Okay, so which of these will have more equations? So node analysis has n minus 1 equations for a circuit with n nodes and b branches. Mesh analysis has b minus n plus 1 equations. So which is likely to be more? Obviously, if you have to solve, you will choose the one with smaller number of equations. Again, many of you have said nodal. Now it depends on the number of branches. Okay, so it very much depends on B, right? And also it depends on the circuit, because for instance I could have a circuit like this. Now these dots are nodes and the rest are branches. You can see that there is a single loop but so many different nodes. Okay, alternatively I could also have things like this. Okay, I have only two nodes but so many loops. Okay, now these are weird cases. Obviously in this case, in the right hand side, when you have only two nodes, you would use nodal analysis, and in this case you would use mesh analysis. There is a single loop. But what happens in a general case is that this now when you have n minus 1, when you have n nodes, right, it's possible that every node is connected to every other node through some branch. Okay, now this is not very likely, but it is very much possible. Now if every node is connected to every other node through a branch, how many branches will we have? Please try and answer this. That is, I have an n node circuit. Now how many branches are there depend very much on the circuit. But obviously the maximum is that every node is connected to every other node. That's possible, right? So in that case, how many branches in total will we have? So I got one answer which said factorial n. Now that is not correct. Okay, so you please think about it. Now we will stop here and we will continue with this in the next lecture. But in the meanwhile, you please think about this. If every node is connected to every other node in the circuit, how many branches will we have in total? Okay. So what we have done today is to discuss mesh analysis, which is an analysis based on KVL for planar circuits, and we also made an analogy with nodal analysis. Okay, so it should be quite easy to understand. We also looked at the exceptional case, which is mesh analysis with current sources, which is analogous to nodal analysis with voltage sources. Okay, So hopefully you have understood it all. Then if you have not understood it, then please raise your questions in the beginning of the next class and we'll discuss them. There is actually a good point here that if n is greater than 4 or 5, doesn't the circuit become non-planar? It is true, it could become non-planar. So let's not worry about node versus mesh analysis. We can talk about node versus loop analysis. Loop analysis can be done even for non-planar circuits. I didn't discuss that because mesh analysis gives you a neat structure, and that's what is usually in most textbooks. So that's why I didn't discuss that. But even a non-planar circuit can be analyzed with loop analysis, and the number of equations you will have to write will be is still b minus n plus 1. Okay. So please think about this. If every node is connected to every other node, how many branches in total? And also please think about everything we have discussed with nodal and mesh analysis. If there are any difficulties, we'll start with that in the next lecture. Thank you. I'll see you on Thursday.